Hello friends, welcome back to course 8. Been a while since I made the last video. Today I'll be making another video of the applied mathematics for engineering series, and today we'll go a little bit into vector integral calculus and its calculations. So today we'll discuss about the surface integral, what's the basic formula of it, and how it is applied in our in engineering a lot. So we'll go into one example, but first of all, we see this basic formula of the surface integral. It's right over here. So if we have a double integral of a surface and we have a vector of force, and we know a certain surface area of it, we could calculate the surface of it by using this formula, or we could exchange some variables into u and v and evaluate this integral into this form. So what's the use of finding surface integrals is very much found a lot in physics. For example, if you want to find fields such as electric fields, surface integrals are usually applied there. So let's just jump into one application over here. So computing the flux of a water. So rather than we go into fields, let's just see one simple example of calculating the flux of water. So here we have our question: compute the flux of water through the parabolic cylinder S y equals to x squared from x from 0 to 4 and z from 0 to 6, and the velocity vector, or our force vector, is as follows: 3z squared 6xz. So our vector here is actually it has unit vectors like I cap, j cap, and k cap, but we don't use it in writing. So what we want to do first is that we want to visualize our problem here. So we have a parabolic cylinder of S, which y equals to x squared. So first we make our Cartesian coordinates of x, y, and z, and we make this red line over here. If you see this red line over here, this is our y equals to x squared. So if you see this from the top view, if you see your eyes from the top over here, you will see that this is actually a normal 2D Cartesian with y equals to x squared, like this, but instead it's vertical. It's laying like on a certain region over here. So this is our y equals to x squared, and we want to evaluate the flux from 0 to 4. So we have this kind of parabolic curve over here, which goes until y equals to 16, because we want to evaluate from 0 to 4, and 4 squared is equal to 16. So this is pretty much our curve over here, and we want to evaluate from 0 to 6. So this is the height of the cylinder. So if you can see a little, if you can imagine a little bit about it, it is like a sort of cylinder, and it is cut into the form like this. So we want to calculate our water flux over here. So we go back to our formula over here. We have double integral of a surface of our velocity vector times this unit vector times dA. But it is pretty hard to find a unit vector over here, and because we need to calculate the unit vector of this flux over here, and it's pretty hard to evaluate the unit vector over here because it's pretty random, because we have this certain region over here which bends, and it makes us a little bit hard to find our unit vector. So you can copy the drawing first and the formula. After this I'm going to clear all of it, and we're going to jump into this formula over here. So we're going to transform a certain form, our case over here, and into variables u and v, and we're going to evaluate the flux. So let's rewrite the formula for that. So integral of a certain region f of r u v dot product of the normal vector in the forms of u and v with respect to u and respect to v. So first things first is we need to evaluate our RUV. So it's our R and in terms of u and v. So we know that we have an equation of y equals to x squared, and we want to evaluate the flux from 0 to 4 from x and 0 to 6 for z. So first we need to change x into u and change z into v. So we take, say, x is equal to u and z is equal to v. Since y equals to x squared, y equals to u squared. So we have our vector over here of RUV, which is equal to xyz. We transform it into u squared, and v. Why is u squared? Just simply because the question asks y is equal to x squared. So y over here is equal to u squared. Pretty simple. And then to find NUV, the formula to find NUV is just RU, the factor of R with derivative respect to U, cross the factor of R with the derivative respective to V. So first we need to evaluate RU. RU is just simply d RUV with respect to U, which is equal to 1 to U and 0. Because if we differentiate U is with respect to U is 1, and U squared with respect to U is 2U, and V with respect to U is equal to 0. So we have our RU factor over here is equal to 1, 2U, and 0. The same thing we do with RV. We take the derivative of RUV, but instead of we take it to U, we take it to respect to V. So it's going to be U doesn't have a variable of V, so it's going to be 0. U squared, take derivative to V, is also 0, and last but not least, V, if we take the derivative to with respect to V, is equal to 1. So we have RU and we have RV. So we need to find the cross product of it. So RU cross RV. You can use Cyrus method for this, for a factor, like using those kinds of what do you say, like diagonal multiplications like that, or you can just put it in your calculator or else, but I'm just going to write the immediate answer for that. So RU cross RV is equal to 2U minus 1 and 0. So we already have accomplished the first, the second part of it. We already accomplished the second, the normal vector with respect to, in terms of U and V, which is this part over here. This is equal to NUV. So what is next is we need to evaluate the velocity vector, but in terms of U and V of the R vector. So you can write it down first. I'm going to clear it up. So in the question, we have f as a function, as the vector velocity is equal to 3z squared 6xz. So if we want to put the velocity vector in terms of u and v, it is just simply substituting z squared with the terms in u and v of the r vector. As before, ruv is equal to u squared and v. This corresponds to x, this corresponds to y, and this corresponds to z. So 3z squared becomes 3v squared. 6, since it doesn't have any variable, it just remains 6. 6xz means 6 times u times v. So we have fruv. So going back to the double integral of a region is fruv dot product of the normal vector in terms of u and v with respect to u and respect to v. So the next step we do is we need to evaluate the dot product of the velocity vector and the normal vector in terms of u and v. So let's just do that quickly. 3v squared 6uv dot our normal vector in terms of u and v is 2u minus 1 and 0. So applying the dot product to it, this becomes 6uv squared minus 6 times minus 1 is minus 6, and 6uv times 0 is 0. So this is our dot product over here. So rewriting the double integral, this becomes double integral of a certain region 6uv squared minus 6 with respect to u and respect to v. In these double integrals, we must look at which variable we want to integrate it first. Since the function over here is closer to du, this means that we are going to integrate this function with respect to u first. And since u corresponds to x, the region that we want to integrate for x is 0 to 4. So let me erase this. So the region we want to integrate for x is from 0 to 4, and it's going to be our first integral. Next, we're going to, after we integrate for x from 0 to 4, we are going to integrate for z, for v, which corresponds to z. For v, which corresponds to z, which is from 0 to 6. So this double integral over here is going to evaluate our flux for the water. So you can write that part in the box, because I'm going to clear it again to make it more easier to see. So we have, let me rewrite that. We have integral from 0 to 4 and 0 to 6 of 6uv squared minus 6 with respect to u and respect to v. So integrating with respect to u, we're going to have 3u squared v squared minus 6u, because 6uv squared minus 6 integrated with respect to u is equal to 3u squared v squared minus 6u. And if you are a bit hesitated about it, you could always differentiate it again with respect to u. If we differentiated to u, we're going to have this function over here again. So 6u v squared minus 6 is just the same thing. So it's correct. And don't forget, we still have one more integral from 0 to 6 for dv. So we enter our boundaries from 0 to 4, and we just input it into u. So this equals to 3 times u squared. 4 squared is just 16 v squared minus 6 times 4 is just 24, minus the zero boundary. The zero boundary doesn't have any effect because 0 times 3 minus 6 times 0 is just 0, so we just don't care about the 0 over here, and this becomes dv. Let me divide this. So this equals to the integral from 0 to 6, 48 v squared minus 24 dv. So we're getting closer to our final answer over here. So let us integrate this function over here with respect to v, and this equals to 16 v to the power of 3 minus 24 v with the boundary from 0 to 6. So this equals to 16 times 6 to the power of 3 minus 24 times 6. And again, we don't care about the 0 over here because it doesn't have any effect, because 16 times 0 minus 24 times 0 is just 0. So this is our final answer for the flux of the water. If you calculate it, it equals to 3312 meter cubic per second. Sorry. So this is the final answer. If you have a different answer, please do comment below, and if you have any questions, please do also post it on the box. And don't forget to subscribe and like the video for more videos, and hope this video helps, and see you next time. Bye.